to welcome everyone to Ganesh Raghunath dissertation defense. He's been here. He was actually one of the last students to start when we had support from Ramiri. So that was a couple years back, and he's been supported by a couple of different projects, but the thread throughout has always been tying back to understanding the auxetic effect in Galfenol alloys. So turn it over to Ganesh, and thank you for coming.
Hello, everyone. Thank you so much for showing up. Thanks for the introduction, Dr. Plato. The title of my dissertation is Characterization and Modeling of the Interaction of Magnetic Fields with the Auxetic Effect in Galfenol. Here's an overview of my talk for today. I'm going to start by giving you guys some introduction, some background on the material and the auxetic effect itself to help appreciate the contributions of the research. And then I'm going to go over 5 major tasks that we performed as a part of this research. First up, let's take a look at the material that we will be discussing today. It's Galfenol. Galfenol is a ferromagnetic smart alloy of iron and gallium. When I say ferromagnetic, it behaves just like iron. So it's not magnetic by itself, but if I put a magnet on it, it starts behaving like a magnet. And it's a smart material because it has inherent magnetomechanical coupling. So for any magnetic input, I get a mechanical output, and for a mechanical input, I would get a magnetic output. And this good magnetomechanical coupling, along with good mechanical properties, which are similar to those of iron, makes it a really good candidate for building sensors. And it has all the other good properties of iron as well. So it's machinable, it's weldable, it's ductile, it's rollable. And here's the second aspect that I'm going to be talking about today. What is auxeticity? I'm sure that everybody has played with rubber bands, and when you stretch the rubber band, it tends to get skinnier. But auxetic materials are those where when you stretch them, they tend to get fatter. And this is very interesting. The Poisson's ratio, which is defined as a negative ratio of lateral strain over longitudinal strain, ends up being negative in the case of auxetic materials because both lateral and the longitudinal strains are positive in this case. Auxetic materials have some really cool applications. Think about a nail that gets thinner and shorter when you hammer it in, and then longer and fatter when you try to pull out. That gives you a good fixture. They've also shown good promise in mitigation of fiber pullout and composites. And there's also, we also expect to see an increase in the indentation resistance of auxetic materials. Auxetic materials are broadly classified into 2 major categories. We have geometric or synthetic auxetics, and we have structural or molecular auxetics. Geometric or synthetic auxetics are usually man-made, and they exhibit a Poisson's ratio of about -10. And these exhibit a negative Poisson's ratio by virtue of how the unit cells that make up the material are linked to one another, mostly using hinges. So when you pull on them, they tend to get broader because of these hinges between the unit cells. In the case of molecular auxetics, the magnitude of the Poisson's ratio is much smaller. It's of the order of 0.1. And it's usually exhibited by cubic metals. And in this case, the negative Poisson's ratio is because of the way in which the atoms that make up the crystal lattice interact with one another. Humans have known about auxetic materials for a number of years now. And contrary to popular belief, more than 69% of cubic metals are known to exhibit a negative Poisson's ratio. But what's interesting is that this effect is shown only in a particular crystallographic direction, which is the 110 direction. And if you look at the chart here, you can see that the values of negative Poisson's ratio are really, really small, except in the case of lithium, of course. But lithium has a really low strength modulus, and you can't really build any applications out of lithium. So let's discuss what the 110 direction actually means. I'm going to give you a brief introduction into Miller indices, which is used by material scientists to define the different crystallographic directions in materials. So when it comes to cubic materials, there are 3 primary crystallographic directions. These are the 100 directions, which are along the edges of the cube. The 110 direction, which is the phase diagonal of the cube, the 6 phase diagonals of the cube. And the 111 directions, which are the body diagonals of the cube. And these primary directions have an associated primary planes, have a primary plane associated with each of these directions. So the 100 directions are the faces of the cube. The 110 direction is a slice made along the phase diagonal of the cube, and the 111 direction is a slice made along the body diagonal of the cube. So with this in mind, we need to, it's important to note that the negative Poisson's ratio is observed along the phase diagonal, or the 110 direction. So one of Dr. Plato's previous grad students, Rick Kellogg, back in Iowa, is it Iowa State or University?
Iowa State.
Iowa State, back at Iowa State. When he was characterizing Galfenol when it was first manufactured at NSWC in Carter Rock, he was trying to characterize the slip planes to be able to build applications using Galfenol. And when he was looking at the different crystallographic directions, he found that when he was doing a tensile test along the 100 direction, he was getting a positive Poisson's ratio, which means there is an increase in the longitudinal strain and a decrease in the lateral strain, as shown on the chart above. But when he was testing the 110 direction, he was getting positive strains along both the longitudinal and the transverse directions. And his first thought was that his strain gauges were broken. But turns out he actually discovered auxeticity in Galfenol. So as you know, Galfenol exhibits auxeticity on the 100 plane along the 110 direction. So it's along the face of one of the faces of the cube, and it's along the diagonal of that face. So if I'm pulling those samples going this way, I would see a positive Poisson's ratio, but whereas if I'm pulling the sample along the diagonal, I would be seeing a negative Poisson's ratio. Another interesting aspect here is that this response is volume conserving, so there's a contraction in the third out of plane direction. So when the 110 directions increase, there is a decrease in the dimension of the 100 direction. So ever since Rick Kellogg discovered this effect, Dr. Flair has had several grad students look at this behavior using different protocols. We had a previous grad student, Holly Schurter, who measured the value of Poisson's ratio using tensile testing in different compositions of Galfenol at varying gallium content. And we also had studies which predicted the values of Poisson's ratio using the elastic modulus that you get from resonant ultrasound spectroscopy. And our collaborators at UC Irvine have developed a density functional theory model which could predict the values of Poisson's ratio for the different gallium compositions. And what they found was very exciting. They found that there's an increasing trend in the auxeticity, or a decrease in the Poisson's ratio with increasing gallium content. And there's pretty good agreement between the three protocols, and we were getting values as low as -0.7. So now let's add the value of Galfenol to the list, and that puts Galfenol at -0.7 right at the bottom. But what really got myself and Dr. Flato excited was, other than being auxetic, iron and nickel also have magnetostriction. And the value of magnetostriction in Galfenol is an order of magnitude larger. And we started wondering if there was a connection. So now is a good point to talk about the direction of research. So up until now, everybody has looked at Galfenol as yet another material which, when you pull along a particular direction, you get a negative Poisson's ratio. But Galfenol has inherently good magnetoelastic coupling. So the questions that we were interested in was, will I be able to see the same effect if I apply a magnetic field instead of tensile stresses? And if I do see this effect, how does it vary at different gallium compositions? And what is the reason for the strains observed, and what is the origin of this effect itself in Galfenol? So to answer these questions, we performed 5 major tasks in this research. We did some analytical modeling, we did finite element simulations, multi-physics simulations. We also ran some experiments to characterize this behavior at different compositions. We did some MOEP microscopy, or magneto-optic Kerr effect microscopy, where we would image the magnetic domains and their evolution to understand this behavior. And finally, we wanted to confirm that we were indeed seeing an improvement in the mechanical properties. So we did some indentation testing. First up, we'll start with the analytical modeling. So this model was able to predict the values of Poisson's ratio at magnetic saturation. So before I go into the model itself, I'm going to give you a brief introduction to the origin of magnetism itself. So magnetism essentially arises from the atomic level itself. So in the simplified Bohr's model, we have a dense nucleus around which we have electrons whizzing around. And since electrons have charge, moving charges have a magnetic moment associated with them, and that is defined by the orbital magnetic moment. And other than this, every electron has a spin moment, an intrinsic spin moment associated with it, and this can take up values, well, not values, this can either be an upspin or a downspin. And the combination of these two defines the net magnetic moment in an atom. Now, does that make all atoms and all elements and all materials magnetic? The answer is actually no, because when these atoms get together to form molecules, they start sharing these electrons, and that evens out the net charge, the net magnetic moment, and we have a balanced molecule. So mostly the elements that exhibit magnetism in nature are lanthanides and actinides, which have a partially filled outer orbit. So let's take a look at the origin of magnetoelastic coupling. So if you look at any of the unbalanced molecules, they have the spin magnetic moment and the orbital magnetic moment. And now when I apply a magnetic field, the spin orbital moment, the spin magnetic moment wants to tip over. And since the spin is rigidly attached to the orbit or the charge cloud, it's going to take the charge cloud with it, and this causes a change in its shape itself because the ions want to shift their positions with respect to the applied magnetic fields. And this is the reason for magnetoelastic coupling. So in the macro scale, all these different dipoles want to align themselves with the applied external magnetic field, and this gives rise to a change in the dimension of the material itself. So in Galfenol, there is an additional anisotropy effect because of the addition of gallium atoms. Iron itself is magnetostrictive, but the value rises up by orders of magnitude when you start adding gallium atoms in there. And the reason for that is the gallium atoms are larger than the iron atoms, and the strength of the iron-iron bonds and the iron-gallium bonds and the gallium-gallium bonds are different. And because of this, there is an additional anisotropy that is being introduced to the system, and this leads to a larger magnetostriction. And this magnetostriction is very dependent on the composition of Galfenol. So the way material scientists look at cubic materials when it comes to magnetostriction is they try and compute or determine the values of lambda 100 and lambda 111. These are called fundamental magnetostrictive quantities because once you know the values of lambda 100 and lambda 111, you can pretty much predict the values along any direction in the cube. So these were experimentally determined values for lambda 100 and lambda 111, and you can find that there's a strong dependence with the composition. We have two big peaks in the magnetostrictive values, and the value is around 400 parts per million, and this occurs at around 18% and 25 to 28% gallium content. And when we hit the first magnetostrictive peak along the 100 direction, we hit 0 point at the in the values of lambda 111. So let's take a look at what happens as I keep adding more and more gallium atoms. So we start out with alpha iron, which is a BCC crystal structure, and it has iron atoms at all the 8 corners, and an iron atom in the middle of the crystal lattice. And now when I start adding gallium, it goes into the A2 phase or the Li2 phase. And these two phases are quite random, and the gallium atom can occupy any point on the crystal lattice. So this happens up until about 12%, past which we start getting partially ordered phases. And these are more interesting to study because when it's very random, you get very random results. So past 12% or around 15%, you would get into the DO3 phase where you have iron atoms at all the corners, and you start having gallium atoms at alternating centers of the unit cells. And as I keep adding more and more gallium, you get into the B2 phase past 20%, where you have a gallium atom at the center of every unit cell in the crystal lattice. Now let's jump into the mathematical model itself. So in any magnetoelastic system, there are 5 major energies that interact with one another. We have the anisotropy energy, and this defines how easy it is to magnetize along a particular crystallographic direction. We have the magnetoelastic energy, and this gives you a measure of how much magnetic energy you will get out of applying stresses and how much elastic energy you would get out of applying magnetic fields. And then you have the elastic energy by virtue of the stiffness present in the material. And you have the magnetic energy because you're changing the magnetic state of the material, and this gives rise to an increase in the magnetic energy. And finally, you have the mechanical energy, which is just a product of stress and strain. So to determine the equilibrium strain, we have to differentiate with respect to the strain. So we get rid of all the terms which don't involve strains. And once I perform the differential, I'm left with that small equation on the right-hand side bottom of the slide. So after energy minimization, when I calculated the equilibrium strain, I find that there are two distinct quantities which add up to form the equilibrium strain. There's a mechanical component and a magnetic component. And since we're going to be discussing the effect of auxeticity only under applied magnetic fields, I'm going to get rid of the mechanical strain component, and I'm going to talk about just the magnetic strain or the magnetostriction. And when I expand for the magnetostrictive strain, I find that I end up with an equation that looks like that. But here's where the trouble is. The values B1 and B2 cannot be determined very easily because they depend on how the electron spins of neighboring atoms interact with one another. So there's no direct way to measure B1 and B2. But you can quantify B1 and B2 in terms of lambda 100 and lambda 111, which are the fundamental magnetostrictive quantities. So when I plug in for B1 and B2, I end up with this really nice equation here, which tells me how much strain I can get along any crystallographic direction for applied magnetic fields along any direction defined by gamma, and I can measure the strain along any direction defined by alpha. So this is really neat for me to be able to calculate the strain along the direction that I'm interested in, which is the 110 direction, and the perpendicular 110 direction, which is called the 11 bar 0 direction. So when I plug in for the direction cosines, I find that the longitudinal strain is defined by 1/4 lambda 100 plus 3/4 of lambda 111, and the transverse strain is 1/4 of lambda 100 minus 3/4 of lambda 111. So I decided to take the negative ratio of these two, and I end up with this cute little equation for figuring out the Poisson's ratio. Now, if I go back to literature, I already know the values, published values of lambda 100 and lambda 111. So I decided to pick values of lambda 100 and lambda 111 and plug it in there. And what I found was very, very exciting, because past the region where you have random phases, you're expected to find Poisson's ratio values as low as -3, which means you're getting 3 times as much strain on the transverse direction as you would get on the along the longitudinal direction. So this was very exciting. And now that we've kind of been able to predict the values of Poisson's ratio at magnetic saturation, we wanted to find out how the strains evolved as we attain magnetic saturation. So to be able to model that, we decided to do some finite element simulations, which involved multi-physics. So we have the mechanical component and the magnetic component talking to one another in the multi-physics simulations. And this was performed using COMSOL. So we had an in-house code which talked to COMSOL to make the simulation work. It used the same energy formulation, but since it's an iterative process, you can vary the magnetic field and get varying values of magnetostriction. So we had an in-house code which could predict the values of magnetic strain and change in magnetic induction for any values of stress and magnetic field that we give as inputs. Once we build up this library, what COMSOL does is you give it a geometry, and then you ask COMSOL to go back into the library and pull out values depending on what inputs you give to the system. So if I know the value of magnetic fields that I'm going to be giving to the system, COMSOL goes back into MATLAB and pulls out the MATLAB library, and then it pulls out values and plots it for us. So we have the elastic boundary value problem, and then we have the magnetic boundary value problem. So we start out by assuming that all stresses are 0. And this gives you a value for the magnetization. And now COMSOL receives an input of magnetic field, and in our case, the stress is 0. And this produces an output of magnetic induction and magnetostriction, which goes into the magnetic boundary value problem. And the output, which would be magnetostriction, goes into the elastic boundary value problem. And this iterative process keeps going on and on and on until we reach convergence in our solutions. So we faced a few challenges. Oops. when it came to the simulations, because the simulation was very, very dependent on the values, the input data that goes into the simulation. And we had 7 major inputs that we had to give to the simulation. So as you can tell, lambda 100 and lambda 111, we did not have some values for the quench samples. And then when it comes to lambda 111, we only had 1 data point for the quench samples, and all my samples were quenched to increase magnetostriction. The values of K1 and K2 are shown in these 2 plots, and as you can tell, again, it's pretty sparsely populated, and I had to interpolate and extrapolate past 20% to be able to get the simulation to work. We had to introduce a smoothing function as well, which is we had to play with the values to make sure that it fits the experimental results. And then finally, magnetic saturation had to be determined experimentally. But the biggest problem that I faced with the simulation was the simulation does not directly account for the thermal history of the sample. So if there was a different kind of protocol that was used to treat the sample, heat treat the sample, it does not directly reflect in the inputs that go into the simulation. So I'm not going to show you the values, the results from the simulation just yet. I'm going to discuss the experimental part of it and compare the results that I got from my experiments with the simulations. So let's jump into the experimental part of the research. So we decided to use single crystal samples of Galfenol with compositions between 12 and 33% gallium. And we got the samples from Ames Lab in Iowa, and they built the sample using a modified Bridgman technique. So once the ingots got here, we checked the composition using Law's X-ray back reflection. Then we cut the dog bones using wire ADM technique, and then we installed bidirectional strain gauges on the dog bones, and we stuck them between the pole pieces of an electromagnet, and we varied the magnetic field. So these were the samples, and you can tell that they're really, really tiny. And so if this is the cube, we wanted to cut a sample which is oriented along the diagonal, and that's how we get those dog bones. So the samples were mounted between the pole pieces of a bias magnet, and we did that using double-sided tape. And we had a feedback loop control to control the magnetic field as we ramped up and ramped down. And although the magnet could do up to 4 Tesla, we only needed about 50 millitesla to saturate all our samples, as in take the samples to magnetic saturation. And this can actually be obtained even by just using a permanent magnet. And the other reason why we didn't want to go past 400 millitesla was we were afraid that the pole pieces might rip the sample away from the stand. So for repeatability purposes, I decided to perform the experiment over multiple trials and over multiple cycles. Each trial involved taking off the strain gauge and putting on a new strain gauge, and each cycle was ramping up and down. So this corresponds to 1 cycle where I went up to 400 millitesla or 4,000 Oersted, and then back down to 0, and that's 1 cycle. And I did at least 5 cycles for each sample. And I at least did 2 trials for each sample. And finally, here are the results from my experimental data. So this was very, very interesting. In samples with less than 20% gallium content, the value of transverse strain was much larger than the value of longitudinal strain, which made the Poisson's ratio value less than -1. So this is very interesting. And you can tell that there is non-monotonic increase in the longitudinal strain and the transverse strain, and the values of the value of strain at magnetic saturation were of the order of tens of parts per million. And that's the chart on the right shows the variation of Poisson's ratio with applied magnetic fields. And at really low values of magnetic field applied, you see some spikes because it's dividing one small value by another small value, which spikes up the value of the ratio. And this just is a cartoon that shows that there is a larger strain along the transverse direction than the longitudinal direction. So this is when there is no magnetic field applied, and that's when we reach magnetic saturation. So we will be discussing more about the non-monotonic increase in the strain values, and we were really intrigued by this because we weren't expecting to see this. And we see this only in samples with less than 20% gallium. In samples with greater than 20% gallium, we see monotonic increase and we reach magnetic saturation. And we did not see the spikes in the Poisson's ratio values at low magnetic fields because it was all monotonic. And this is what we had expected to see from all the samples, but we saw those weird anomalous behavior. And in samples greater than 20% gallium, you can see that the longitudinal strain is larger than the transverse strain, and that puts a Poisson's ratio value greater than -1. This chart shows you raw data from all the samples. It's too cluttered up. I'm not going to go into the details of this. So here's comparison with the multiphysics simulation. So the simulation was able to predict the values at magnetic saturation pretty darn well. The error percentage was less than 10% at magnetic saturation. It was also able to predict the non-monotonic increase that you see in the strains along the longitudinal direction, but it didn't predict the decrease that we observed along the transverse direction. But this was very exciting because this, this could actually predict the trends in the strains, and we did not see this small weird bump in the longitudinal direction where we did the simulations at greater than 20%. And the value of Poisson's ratio at magnetic saturation was also less than 10% in terms of error when compared to the experimental data. So this is a summary of all the work that I did. It shows you the values obtained from the experiments. It compares it to the value that I obtained from the analytical model and the multiphysics simulations. And as you can tell, they're all in pretty good correlation with one another. But what's important is that in samples between 20 and 25%, the values of strains were so small that we were very close to 0. And sometimes because of drift, I was seeing values that were positive. So because I was able to do so many cycles and so many trials, I was able to come up with good error bars for the values that I obtained for Poisson's ratio at magnetic saturation. So here's the interesting part. Now we have the data, so we were trying to understand what's going on. So when we compared the data that I obtained with applied magnetic fields and 0 applied stresses with the values that were obtained earlier by other researchers under applied tensile loads and 0 magnetic fields, you see that there is an opposite trend. You see a decrease in the value of Poisson's ratio with increasing gallium content, whereas at magnetic saturation, I was seeing a decrease in the auxetic effect with increasing gallium content. So this got us thinking. So we decided to, we kind of came up with a reasoning for why this is, why we see this behavior. So in terms of when we do tensile testing,
can you go back two slides back?
Okay, sure.
So let's see, you're getting the green triangle is the experimental data.
Mm-hmm.
So why didn't you measure the other ones? Because that's well known or something? The lower gallium concentration?
Yeah, that's at, so less than 12% is very random.
Random?
Yeah, in terms of where the gallium atom occupies the lattice.
Oh, I see. So
Because of A2 phase.
But experimentally, what do you get?
Oh, I did not have samples at less than 20%.
Oh, I see.
I tested between 12% and 33% gallium.
So because of the atomic ordering?
Yes. And the other reason is the values of strains are going to be really small because the more gallium I add, that's when I see the first peak in magnetostriction. So the values are going to be really small in terms of strain.
What supports the idea of atomic ordering?
Depending on where the gallium atoms occupy, the lattice points that the gallium atoms themselves occupy, that determines how much magnetostriction that I would get. And that determines how much strain I would get along the longitudinal and the transverse 1 and 0 direction. And the ratio of that will determine the Poisson's ratio, which is what I'm presenting here.
Gallium ordering means that one gallium has a fixed position with respect to the neighboring gallium. Is that correct?
Right.
So how do you know that is true?
How do I know that is true? Because
suppose one gallium sits in the center of the unit cell.
Right.
So the next gallium also sits in the center.
Right.
The both.
It depends on the phase in which you are. Right. As you keep varying the gallium content, you go from one.
BCC, that stuff.
Yes, it's always BCC, but the point that the lattice point that the gallium atoms occupy is going to depend on the composition. You start with A2 phase, and then you move into DO3,
So how do
and
you
then
know that?
that's been established. Well, the NSWC folks have pretty
Okay, fine.
well-defined curves for that.
Okay.
All right. So going back, so we see an opposite trend between applied mechanical loads and magnetic fields. So to understand this, let's look at the energies that are involved in the magnetoelastic system. We have the anisotropy energy, the magnetoelastic energy, and the magnetic energies. And when it comes to applied tensile loads, we don't really apply any magnetic energy, so we're going to take that term out. And as the gallium content increases, we know that the anisotropy decreases from the curves that I showed when I was discussing the drawbacks of the simulations. And when anisotropy decreases, the magnetoelastic energy increases because of the applied stresses. And when this happens, this leads to lattice softening. And from a metallurgical perspective, as we keep adding more and more gallium in the alloy, it starts behaving more like a mixture of metals or a metalloid instead of an alloy. And this leads to a reduction in the number of iron bonds, and this leads to lattice softening as well. So when as the gallium content keeps increasing, it gets easier for me to pull, and that leads to higher values of Poisson's of negative Poisson's ratio. But what happens when I apply magnetic fields? For some reason, the boxes are offset by a little, but never mind. But anyways, the total energy is still the same, but since we don't apply any stresses, we don't have any magnetoelastic energy, and we have magnetic energy going into the system from the applied magnetic fields. So as the gallium content increases, anisotropy still decreases, and the magnetic energy increases, and this restricts lattice softening, because the more magnetic energy there is in the system, the more the atoms interact with one another and try to stick together, and that increases restriction of lattice softening. So interestingly, a previous postdoc, Jin Yu, from our group, he measured the values of Poisson's ratio under applied tensile loads under the presence of a DC magnetic field. And the red dots show the values that he got experimentally. So if I compare this with the values that Rick Kellogg got under applied tensile loads under zero magnetic fields, and the values that I get with applied magnetic fields and zero tensile loads, we find a very interesting phenomenon. The values of Dr. Yu are right between the values that I predicted for zero applied tensile loads and the values that Rick Kellogg had predicted. So this kind of confirms the fact that the magnetic energy and the mechanical energy are competing with one another in the magnetoelastic system. So if one is leading to lattice restriction, the other one is leading to lattice softening, and that is the reason why Dr. Yu's data falls right in between mine and Rick Kellogg's. So what else can we do with the results that we obtained? Using the values of longitudinal and transverse strain at saturation, you can actually play around with the numbers and be able to predict the values of lambda 100 and lambda 111. It just allows us to solve because we have two equations and two unknowns. And this is really interesting because now we can predict the values of lambda, well, it's not predict, it's experimentally determining the values of lambda 100 and lambda 111, which are the fundamental magnetorestrictive quantities, by having values of values of strain at magnetic saturation along the diagonal instead of along the edge of the cube. And as you can tell, there is pretty good correlation in both the values of lambda 100 and lambda 111 when compared with literature. And this is the first curve that gives you that populates the lambda 111 curve for 20 samples of Galfenol. Now to the interesting part. So we still haven't discussed about why we see a monotonic, non-monotonic increase in the longitudinal and the transverse strains. And so to understand what's going on, we decided to split up the strain curve into 4 distinct regions. We have region A, where there is increase in both the longitudinal and the transverse strains. We have region B, where there's a sharp increase in the transverse strain, but a decrease in the longitudinal strain. And pass B, there's a decrease in the transverse strain and an increase in the longitudinal strain. And pass D, we achieved magnetic saturation. So we decided to propose a magnetic model which could, based on how the dipoles would, the magnetic dipoles would interact with applied magnetic fields in Galfenol. So we start at 0, and we assume a perfectly demagnetized state. So all the magnetic dipoles are randomly oriented such that the overall energy in the system is minimized. And when we start putting in energy, because of anisotropy, we know that the 100 direction is the easy direction. So even if I put in energy, magnetic energy along the diagonal, the energy still wants to flow along the edges of the cube. So that orients the dipoles along the 100 directions, which are easier to achieve. And now as I keep adding more and more energy along the 110 direction, that's going to cause some of the dipoles to start flipping over along the direction of applied field, which is the longitudinal 100 direction. And then we achieve magnetic saturation past D, where we have all the dipoles oriented along the applied magnetic field. But we didn't want to stop with just proposing a model. We wanted to make sure that what we're proposing is right. So we decided to do some Kerr imaging to see how the magnetic domains evolved under the application of magnetic fields along the 110 direction. Let me give you a little bit of background on how magnetic domains work. So in non-magnetic materials, we don't worry about the magnetic dipoles, but in magnetic materials, there are regions where there's a nominal direction for the magnetic dipoles, and these regions are grouped together and called domains. And now when I apply a magnetic field, the dipoles in the domains, they rotate to orient themselves along the applied magnetic field. Here's the MOAC microscope. So it essentially uses optical white light, and we have a polarizer and an analyzer. So when the light bounces off the sample, because of these different domains being oriented in the different directions, polarized light, the angle of polarization of the polarized light changes. And when we observe through the analyzer, we find that there is a contrast in the images depending on the orientation of the domains on the sample. So we put the sample on the stage, and we mounted it between the pole pieces of an electromagnet, and we varied the voltage. So here's a sample that I use. I use the same sample that I use for my magnetostriction measurement. And I installed a bidirectional strain gauge rosette on one side, and then on the other side, I polished it. It's very hard to polish. It's very hard to attain a good surface condition, because it's very essential that we have perfect surface conditions to do MOAC imaging. So it took me about 18 hours of mechanical polishing, and finally I was able to get a sample which had good enough surface conditions for MOAC measurements. So these are the 4 distinct regions that I talked about earlier, and these are the red lines depict the values at which I decided to take pictures or get the images of the magnetic domains. I wanted to take a picture at the starting and the ending point of every region that I have on the strain curve. And this was very fascinating. So for the first time, I was able to get magnetic domain images of Galfenol along the 110 with magnetic field being applied along the 110 direction. So at 0 field, there seems to be some sort of a uniaxial anisotropy. So instead of having the dipoles oriented, the domains oriented along all the 4 easily favorable, the favored 100 directions, we just have the domains oriented along a particular 100 direction. For small applied fields, the pin domain walls, the domains grow, bulge and go back to where they were. And for more magnetic field, the favorable domain. So in this case, I'm applying a field going that way. So this is not favored, and this is favored. So you can see this growing bigger and bigger until we reach a point which is C, which is right there. And past C, for an applied magnetic field, what seems to happen is this seems to rotate to orient itself along the applied magnetic field. So from being oriented along the 100 direction, we're now oriented along the 110 direction. And as I keep applying more and more field, the unfavorable 110 diminishes, and we attain magnetic saturation at F. So based on what we saw here, we had to modify the proposed model. So instead of so this is the modification that we had to come up with. Instead of having it go along the 100 directions and the 110 directions, we had it go along the 100 directions alone, and then flip over completely to orient themselves along the 110 direction. So this makes it easier for me to explain this. So this is the proposed mechanism, and it turns out that there's something going on between stages A and B and C as well that wasn't expected. So the way in which we need to understand what's going on in Galfenol is, at small magnetic fields, there's a rotation of the dipoles to orient themselves along the applied magnetic fields, and this is the reason for the large increase in the transverse strain. And past 10 millitesla, past region B, it seems to behave like a regular material where there's an increase in the longitudinal strain and a decrease in the lateral strain. So magnetostriction in Galfenol occurs as a burst along the 110 direction, and since it's already achieved a large value of transverse strain, we continue to be auxetic even though there's a shrink along the transverse direction. So this was very exciting for us, and we modified the dipole mechanism that we proposed earlier. So the takeaway point up until now is there is an auxetic effect, and that's been established. We've been able to predict the values, but the values of strain themselves are really, really small. So this restricts the potential applications. We only get tens of microstrains. So we can use it for optical corrections and stuff like that. But what is really interesting is, if the Poisson's ratio value goes down to -1, it's going to cause an increase in the mechanical properties. And now this leads to a lot of potential for applications. So we wanted to confirm that we indeed saw an increase in the mechanical properties of Galfenol as we reached Poisson's ratio values close to -1. So this is just the Hooke's law. You have the 36 independent components for the stiffness. But since we're dealing with a cubic material, we only have 3 independent elastic constants. A previous researcher had derived the dependence of the 110 the Poisson's ratio along the 110 direction in terms of these elastic coefficients. And what I decided to do was to rearrange the terms such that we're able to compute the Zener ratio, which is the measure of anisotropy in the system. So in isotropic materials, this ratio goes to 1. And this essentially determines the shear strength of the materials, because C11 minus C12 over 2 is the tetrahedral shear modulus, and C44 is the diagonal shear modulus. And the ratio of this gives you the Zener ratio, which determines how resistant the material can be for shear. So when I rearrange the terms, it turns out that Z is proportional to 1 over 1 minus Poisson's ratio over 1 plus Poisson's ratio. And there was a previous work by Alderson, who works on auxetic foams, which is a synthetic auxetic, and he showed that the hardness value of anisotropic foams is proportional to 1 over 1 minus Poisson's ratio squared. So in order to confirm that we indeed see an increase in the mechanical properties, we decided to do indentation testing. So if I plot the values 1 over 1 minus nu over 1 plus nu and 1 over 1 minus nu squared, you can see that at 0 Poisson's ratio, you're right here on the curve. And for a small increase in the Poisson's ratio, you get a small increase in these mechanical properties. But as these values tend closer and closer to -1, you get really large increases in the magnitude of shear resistance and hardness. So for isotropic materials, the shear resistance varies as 1 over 1 plus nu. And since we have an anisotropic system, it's 1 minus nu over 1 plus nu, which is a sharper increase in the value of mechanical properties. So we decided to stick our samples into a nano indenter, and we did some Vickers hardness testing. So we tested the sample with and without a magnetic field. So we put a permanent magnet right next to the sample, and we indented it, and then we also tested it without the presence of a magnetic field. And the results that we got were very, very exciting. I actually got these results just last week, well, 2 days back, actually. So the Vickers hardness for iron is 600 megapascals. And the value of hardness for Galfenol has to be slightly lower because it's a softer alloy, because gallium is softer than iron. And we found that the value without a magnetic field is between 400 and 700 megapascals, and the average was around 550 megapascals. But when we applied a magnetic field, so this was done on the 18% gallium sample, where the value of Poisson's ratio at magnetic saturation was the closest to -1. So when the value was closest to -1, and when I put a bias magnet right next to it, and then when I indent it, the value went up to around 1.5 gigapascals, which is 3 times larger than what I was getting without the applied magnetic fields. So this was very exciting, and it proves that there is indeed an increase in the mechanical properties as we get to Poisson's ratio values close to -1. So this kind of opens up a lot of potential applications. If we can tune the value of Poisson's ratio to be around -1 by applying magnetic fields, now that way we can keep these mechanical properties really, really high. And we can build a lot of potential applications using this. So in conclusion, we observed a Poisson's ratio value close to less than -2.5 in Galfenol. And we were able to develop a mathematical model that could predict the value at magnetic saturation. The predicted values from the analytical model and the multi-physics simulation were in good correlation with the values that we obtained from the experimental data. We were able to use curve microscopy to understand the magnetic evolution of magnetic domains while the samples were exhibiting a negative Poisson's ratio. And we use results from nano indentation to prove that there is an increase in the mechanical properties when we reach values close to -1 in Auxetic Galfenol. For future work, we're planning on writing up a proposal with Dr. Woodig, and we're trying to get beam time at a synchrotron in Chicago. And that would mean that we can actually see these atoms move apart from one another. And because auxeticity is so scalable, what happens at the atomic level really scales up at the macro level. And if we can see the atoms move, interact with one another under applied magnetic fields, that would be really exciting. Our collaborators at UC Irvine, they're working on a density functional theory model that could predict the values of Poisson's ratio under applied magnetic fields alone. And what would be the ultimate goal of this research would be to be able to build magnetically tunable load-bearing auxetic structures using Galfenol. And finally, we're writing a proposal which would investigate the effect of adding auxetic inclusions into composite materials. Here are the contributions of the research. This is the first research ever to look at auxeticity in materials with applied magnetic fields. So traditionally, auxeticity has been associated with just stretching, and now we're able to show that there is auxetic effect by applying magnetic fields. We were able to develop the analytical model, the multi-physics model. We used, this is the first time that anybody has used curve microscopy to understand the evolution of magnetic domains along the 110 direction. We were also able to derive information about the second peak of magnetostriction, which still is an area of study which has been unexplored in Galfenol. I also came up with a new protocol for polishing. So traditionally for polishing, when you polish for moke, people have been using acids to etch the sample. This kind of eats away a lot of material, and your sample is not the same before and after moke. But I was able to come up with a protocol where I can eliminate the use of etching when you polish for moke. And this study was able to give more insights into why Dr. Yu was seeing lower values when he was using a DC magnetic field while doing tensile tests. And finally, nano indentation tests under the application of magnetic fields. This is something that nobody has ever done before. Here are some publications. I'm really excited about the one that we just turned in. This is to the International Conference on Auxetics in Malta. And we're probably the only group where we have smart materials which show auxetic effect under magnetic fields in the entire conference. Finally, I'd like to thank my sponsors, ONR Muri, the NSF, and NAVAIR. And I'd like to thank everybody that I've ever interacted with over grad school. I'd like to thank Dr. Flato for being an amazing advisor and a great motivator. Thanks to Dr. Worley, Lee, Dr. Takeuchi, Dr. Woodig, and especially Dr. Woodig, because Dr. Baz couldn't be available today, so he was willing to step in for him. And a special shout out to Dr. Na, who couldn't make it today. He was the best office mate that I've ever had. and Dr. Park and Dr. Yu, the other two postdocs in my group. I've learned a lot from these two. And previous grad students, Chaitanya, Supratik, Atul, and Hyunsuk. I've had some really, really good conversations with them about Galfenol. I wasn't in grad school when Atul and Supratik were here, but even afterwards, when we met at conferences, we always had very scintillating conversations about Galfenol. And I'd also like to thank Zohaib and Lena, and previous grad students in the group, Michael Marania, Daryl Douglas, Brett Barkley, Aaron Sassoon, Peter, Steve, and the current grad student, Michael Van Order, and the entire Aerosmart team. We've worked with a lot of undergrads, and I'd like to thank everybody. I'd also like to thank my collaborators, Ashish, Ken and Jackie at Naver, the folks at Carter Rock and Etrima Products and Ames Lab for making these samples. And a special shout out to the Aero office people. Without them, grad school can never be smooth. Finally, thanks for your patience and your interest in my research. I'm glad that you all came. I'll be glad to take questions.
Did you calibrate your COMSOL software?
What do you mean by
I mean, you stuck in a system that you know the answer, and then you let COMSOL do it, and if it doesn't give the answer you already know, then COMSOL is maybe good or not good, I don't know.
So the thing is, we didn't really use a solver. What essentially COMSOL did was we built our own in-house code which could predict the values, and then COMSOL just goes back into the code and pulls out values and plots it for you for the different geometries. So we're not really using COMSOL as the main solver here. It's mostly for going back in and pulling out values from the library that we had already built.
I have one more question, then I'll shut up. If you, you presented a lot of magnetoelastic data. How does the magnetization curve look like of this material?
I haven't. Are you talking about the simulations?
Yeah, and compare it with the.
I haven't looked at that. I haven't looked at magnetization directly. No. But I think it's just a small step away because the simulations already calculate the magnetizations at the different applied field values. But what I was more interested in was the strains that I got and the way in which the Poisson's ratio, the ratio of the the ratio of the strains and Poisson's ratio. And that was more of my concentration than the magnetization itself.
So when you sorry, I break my promise. And you calculated Poisson's ratio as on the basis of elastic constants, right?
No. My Poisson's ratio.
I mean, you get it 1 over 1 minus theta square or something, and the ingredient for theta square was the ratio of elastic
No.
It's based on magnet restriction.
Yes, it was based on magnet restriction, not on the elastic constants.
Kellogg's was based on elastic constants.
Right, Kellogg's, that was his one.
But I think we discussed this last time. So this is magnetic field induced auxicities?
Yes. So it is not auxeticity in the traditional sense, which is what makes this special.
So without magnetic field, is there any way to achieve this large number?
No, actually,
It's an extrinsic.
the only way in which you can, so it's either you add mechanical energy or you add magnetic energy to the magnetoelastic system. And with mechanical energy, which is tensile loads, Kellogg and Hawley, they've already calculated all the data that you can get. And they found that the value of Poisson's ratio, is as low as minus 0.7. But under magnetic fields, you're able to get values as low as minus 3.
What I mean is, are there any other mechanisms? Because you have a list of materials. I guess other than this, based on your table, lithium has the largest.
Right. But you can't really.
Is there any? So what's happening in lithium there? Because that's also pretty large, right?
Well, it's
almost
minus
the same order.
it's minus 0.5, and that value was determined by tensile testing, not from applied magnetic fields. So some of these samples, lithium and copper and all these other elements, they don't show magnetic characteristics. So you can't really achieve this by applying magnetic fields. Because applying magnetic fields is what makes this really unique, because you don't have to touch the sample, and you can just apply a magnetic field and see this phenomenon happening.
What happens if you take the magnetic field off?
It just goes back down to 0. You don't see any strains, so you don't have a Poisson
you
solution.
get those super values only under an applied field.
Yes. Yes. You can also get this if you apply a pre-stress. So if you check the indentation values with the pre-stress and without a pre-stress, you will still see an increase along
If
with
you
1
take the pre-stress away?
It goes back to 0.
So then in principle, if you could do this with a terphenol,
You cannot, because it's brittle.
if you
Not
can.
cubic, not cubic.
And it's not cubic as well. Yeah. So you don't have the 110 direction. Yes, Dr.
What happens when you add thermal energy?
So Galfenol is pretty stable thermally, so until 600 degrees Celsius, you don't really see a decrease in performance. So I would expect to see the same performance up to a large temperature. Yes.
When you talk about making structurally load-bearing
Mm-hmm.
items out of Galfenol,
Mm-hmm.
would those be solid Galfenol or some kind of coating, or
So,
whenever
yes.
you make Galfenol, is it a thin coating?
Great question. So we've been able to develop textured Galfenol, which is as good as single crystal Galfenol, but we're still, fine-tuning our protocol to get good quality material. And once we get that, that makes the cost really go down, because iron is really cheap. And if we can build rolled sheets, that makes it really, really exciting. And sheet is better than bulk samples where you cut out sheets. So yeah. And we've also started looking at inclusions. We powder Galfenol and put it into a matrix, and we check properties. That's something that one of the postdocs has just started doing. So
What's the melting point of this?
oh, it's very, very high. I don't thousands, I guess.
Yes.
Celsius?
Fif-
Yes,
fif-
Celsius.
1500.
1500. But I think Dr. Na can
Yeah.
go up to 1500 and just lose. You end up. So gallium tends to evaporate when you go to really high temperatures,
Yeah.
and melting point should be much higher.
Yeah.
Definitely larger than 1500.
Yeah, Neil's at 1250.
Yeah, 1250. So it should be much higher than that.
So what type of application
Yes.
do you
So.
envision?
So if we can, so as I told you earlier, the strain values itself are of the order of tens of parts per million. So you can't really expect to move a lot of stuff. So it's not going to be a great actuator. Maybe you can use it for optical corrections and microscopes and stuff like that. But what's really interesting is the increase in the mechanical response at these Poisson's ratio values. So you can apply so in samples where you can reach values less than -1, there's some particular value of magnetic field where you actually get to -1. So if the Poisson's, let me go back and explain what I'm talking about. This is actually a really great question, because that's actually a big contribution from this work. It'll take me a while, sorry about that. Okay. So as you can tell, when the values are less than -1, you have to go through a point where it is -1, right?
Yeah.
So if you can figure out that value of magnetic field, you can tune the structure so that the value of Poisson's ratio continues to be at -1 even under applied loads, and that would mean it's going to be really, really rigid, and that's very exciting.
Yeah. What is your specimen?
What is my specimen? Oh,
That's the size. What's the smaller size of a specimen, right?
that. So
Yeah,
these are the
yeah.
specimens that I
So
use
then-
for.
then how much energy the say in terms of electricity? How much energy was put in?
Electricity.
I'm just asking how much. How much?
Permanent magnets.
Huh?
Yeah, I mean that's the whole point. I mean, you can saturate this using permanent magnets.
Oh, it's permanent magnet.
Yeah, yeah. So the indentation tests were performed using
So
permanent
how
magnets.
big was the permanent magnet?
It was really small. It was as big as a sample, which is about 0.1 millimeters by 0.1 millimeters, which is why we had to do nano indentation.
Plain making, this is a huge magnet, the one you're showing right here in your picture.
Yes, which is why I mentioned down below, this can be achieved by just using a permanent magnet because we only need 15 millitesla to saturate the samples. This is an overkill, basically, but this gives me the ability to ramp up and down the voltage. I don't want to be taking off permanent magnets and putting a new one back on to get the strains at different magnetic fields. Yes.
Did you say any recommendations about future work? Like what's next?
Yes, yes. So we're planning to test these samples in a synchrotron and
Oh yeah.
under applied magnetic
I
fields and
remember.
see if the atoms actually move.
Okay, I remember that.
Yeah.
There was a bunch of collaborators.
Yes, yes. Yeah, we're still trying to get the proposal in to be able to get beam time on the synchrotron, which is
Did you ask students to ask questions?
no, I didn't actually.
Did you invite students to, or give them incentives to ask questions?
Well,
Like
there's a lot of food
like
outside.
a chocolate.
Yes, Andrew.
At the beginning of the presentation, you said that, although I think, if I'm understanding correctly, the Poisson's ratio means that you get expansion in the lateral and transverse directions. There's volume conservation, so in the other direction, you have to decrease.
Yes.
So how does that, I guess, where does that come out if you're trying to build structural members out of this?
What do you mean by where does it come
Well,
out?
like if you stretch, a structure, or you compress a structure in one direction, and the Poisson's ratio and auxeticity make
Measured
it
on the
very
plane.
stiff.
Yep.
Where does the volume conservation come in that
So,
area?
so if you look at if you take a rectangle,
Yeah.
the thickness is going to decrease. The length and width will increase, but the thickness will decrease.
Okay.
And this kind of ties in pretty nicely because when you indent on that plane, because of the reduction in the thickness, I think it's getting denser, and that's the reason why the mechanical properties are going up. That's another way to look at this.
So then you can define the Poisson's ratio in that direction too, right?
Yes, that's what this study tells you.
So then so then the Poisson's ratio must be really large in the other direction. Because auxeticity is of a record value, then the Poisson's ratio, because it just goes in the opposite direction because it's a volume conserving.
Yes.
Is that correct?
Yes.
So why don't you, auxeticity is more important than extremely large Poisson's ratio? Because they go together, right?
They go together. Yeah. So you don't get the negative. You get a positive Poisson's ratio if you measure in the perpendicular direction.
Right.
The 1,001,110,100
But supposedly that value is much, much larger, like an order of magnitude larger than normal material.
Yeah, which goes back to this plot. So you're saying the value could be really large out here, right?
Yeah. So it's not equally as important in application than.
It is, yeah. I actually have some preliminary indentation data for that particular direction. I haven't gotten a chance to look at the numbers yet, but I checked along, the auxetic plane and the perpendicular plane, just to be sure that there is an increase. But this was really exciting, so I put it on my slides. But I haven't looked at the values for that one yet.
So we'll add then. The samples were too thin to gauge in that direction, but we. So
Yeah,
there's
we can't
nothing-
use a gauge,
but-
which is
but-
why
but
we
you could use
decided
as
to
models.
use indentation
Yeah,
testing.
yeah, you could
Yeah.
use as models. yeah.
And I think this geometric thing is a good sort of analogy to understand the effect. But
Yes.
there it's not like volume conserving, right?
No, so
It's
most
just a
of the
geometrical trick, right?
Yes, it's
So
a
there's
geometry.
nothing to do with. You could make like a pop-up book. And
Yeah, exactly. That's
authenticity could be infinite or something,
Yes,
right? So
yes.
that's kind of not a.
and they can't. So those are mostly sheets, and they can't really take any loads. So this is very exciting because Galfenol can take loads. It's as good as iron in taking loads. And those cannot take loads. If you put a load on it, it just tears. But there have been auxetic foams where there is volumetric negative Poisson's ratio. It's not volume conserving in some of the foams, and they have shown increase. Yes, yes, and they have shown some. They've shown increase in the mechanical properties as well. So that's from where I picked up the equation for the hardness. It's a work by Alderson.
Can you go back to page 23?
23.
Yeah.
Can you escape?
Yeah, it's faster that way. Yep.
Okay, the last line in the equation.
Mm-hmm.
So the first term is 1/2 epsilon transpose C epsilon.
Mm-hmm.
That's the strain energy associated with strain.
Yep.
What's the last term? Sigma T times epsilon.
So that occurs, when you apply a mechanical stress and
So
there's a strain.
sigma is the applied stress.
Yes. Yes.
Okay. All right. Okay.
Any other questions from the audience? We will ask the audience to step out and ask the committee to remain